Welcome back to another Explainer, strategists. Today we are engineering the perfect DNA of an exam answer. We're diving straight into Cambridge AS level physics, specifically targeting syllabus 9702, but frankly, if you are sitting 0625, 0652, 0654, 0972, or 5054, you need this exact strategy. We are mastering the mechanics of turning forces and statics, but we aren't just memorizing formulas today. I want to introduce you to two very typical students. First, there's Alex. Alex overloads every single answer with massive amounts of raw physics facts, writing absolute essays, but provides zero actual analysis. The examiner gets exhausted just looking at it. Then we have Sam. Sam rushes through the paper, completely misses the specific command word requirements, and throws away easy marks because of it. Have you ever looked at a complex diagram of forces and felt a bit lost, falling into the trap of being an Alex or a Sam? Don't worry. By the end of the session, you'll see exactly how forces interact to create balance and rotation, entirely through the power of our proven physics success blueprint.
Okay, let's dive into a feeling you already know. Have you ever tried balancing a meter stick on one single finger? You shift it left, you shift it right, over and over, until suddenly, it just sits there, perfectly still. It feels like magic, but it's pure physics. You already intuitively understand the core concept we are going to tear apart today. But here's the problem. Intuition doesn't score marks. If the exam asks you to explain that balance, Sam would write, "It balances because the middle is supported." 0 marks. Alex would write a whole page about the history of the meter stick and gravitational pull across the solar system. Also 0 marks. Our goal right now is to translate that exact everyday intuition you have in your fingertips into the precise, rigorous terminology and assessment objectives you need to secure an A-star. We are going to turn those red pen marks into green check marks.
Here is exactly how we're breaking this down today to build your perfect answer structure. First, we'll explore the center of gravity, and we'll apply our Peel framework. That's point, evidence, explanation, link, to definitions. Second, we will look at the turning effect and break down exactly what the command words are asking you to do. And third, we'll put it all together by solving a forces problem under timed conditions, showing you exactly how top students structure their mathematical answers without dropping a single unit mark. We are logically progressing from the basic concept of weight acting on a point, all the way to breaking down a complex, high-mark worked example.
Let's start with the first section on our agenda and look at exactly how objects balance. This is the foundation of statics. Without mastering this, everything else we do today will literally fall apart. Get your notebooks ready because we are about to decode the assessment objectives behind this fundamental concept.
Think back to that balancing meter stick. When an object balances at a pivot point, it doesn't turn. Why? Because the weight on one side of your finger is perfectly matched by the weight on the other side. Supporting the object at that pivot means the only force you actually have to apply is an upward force to stop the whole thing from crashing down. And that upward force? It is exactly equal to the total weight of the entire object. This is your point and explanation in the Peel framework. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Seriously, mastering these foundational frameworks is how you secure those top grade boundaries, so make sure you are locked in for every single explainer we drop.
So the crucial takeaway here is this exact syllabus-approved definition. Center of gravity, the point at which the whole weight of the object may be considered to act. When the command word is defined, this is all the examiner wants. They do not want Alex's essay. They want this precise sentence. Even though every single microscopic particle of that stick has its own tiny bit of weight, physically and mathematically, we can consider the entire weight of the object to act at just one single balance point, acting vertically downwards. When you draw your force diagrams, which is a classic assessment objective, the weight of an object is always shown as a single force arrow pointing straight down, originating exacting from this specific coordinate.
Now, finding this point experimentally can be tricky for odd, irregular shapes, and that's a different exam question entirely. But for the core mechanics problems in your AS level exams, you are almost always dealing with uniform objects. Think of a perfectly uniform ruler or a solid metal rod. For these, you can always safely assume the center of gravity sits exactly at its geometrical center. It is a wonderfully simple rule, but it is the foundational assumption you have to make for almost every statics problem you will face. Don't overcomplicate it like Alex would. If it's uniform, find the middle. That's your point of action.
Now let's move to our next core concept and see how this builds into the idea of a turning effect. Because what happens when you don't support an object exactly at its perfect center of gravity? Things start to get dynamic, and the mark scheme gets a lot more rigorous.
Up until now in your physics journey, you've likely spent a massive amount of time calculating how a force pushes or pulls an object in a straight line. Think Newton's second law, F equals ma. But a force doesn't just push things in straight lines. As this comparison brilliantly illustrates, if an object is pinned or fixed at a point, what we call a pivot, applying a force will actually cause the object to rotate or spin around that pivot. Now, I want to initiate our first interactive workshop challenge right now. Let's call it the data scan. Imagine there's a 60-second visual countdown timer right here. Look at the text comparison on screen. I want you to mentally extract the core trend here. The difference between linear and rotational motion isn't the force itself. It's the presence of a pivot point. That is the crucial distinguishing factor you need to state when explaining rotational mechanics.
Now for our second interactive challenge, find the flaw. I'm going to tell you what Sam wrote on a mock exam based on this slide. Sam wrote, to make the turning effect bigger, just move the weight, change the weight, or tilt the ruler. What's the flaw there? It completely lacks precision. Let's look at the actual variables. If you hold a horizontal meter rule, you can physically feel that the turning effect increases if you do three very specific things. First, adding more weight, which increases the magnitude of the force. Second, moving the exact same weight further away from the pivot point. Or third, changing the angle of the ruler toward the horizontal. As the angle approaches 90 degrees to the force, the effect maximizes. Precision in your language is what separates a B grade from an A star.
Now, what is really interesting about this slide is how it formalizes that physical twisting feeling in your wrist into the exact Cambridge definition of a moment. A moment is the turning effect of a force. But look at the precise wording. It is the product of the force and the perpendicular distance of the line of action of the force from the pivot. That word perpendicular is the absolute trap where thousands of students lose marks every single year. It is not just any distance. It must be defined precisely at a right angle to the line of action. If you omit the word perpendicular in a definition question, you will drop the mark. Guaranteed.
Let's look at the mathematical translation. Moment equals force times perpendicular distance, or F times d. And because we are multiplying a force measured in newtons by a distance measured in meters, the unit is strictly the Newton meter, or Nm. Let's do challenge 3 right now, speed writing. You have 30 seconds to mentally write one perfect Peel paragraph explaining this formula. Ready? Point. A moment calculates rotational force. Evidence. The formula is force times perpendicular distance. Explanation. This shows that both the magnitude of the push and its leverage distance equally impact the rotation. Link. Therefore, maximizing either variable maximizes the Newton meters generated. That is how you engineer a perfect answer, my friends.
We have the definitions. We have the frameworks. Now let's put this into practice and deconstruct a complex forces problem together. But right before we calculate, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's execute our time management matrix on this scenario. When you see a word problem like this, you shouldn't just stare at it. You need to immediately visualize and annotate. Picture a light rod. Let's call the ends A and B. It has a total length of 45 centimeters. It is being held at point A, making A our pivot. The rod is tilted so it sits at an angle of 65 degrees to the vertical. Finally, a 15 Newton vertical downward force is pulling on the end at point B. Your brain should immediately be flagging the key variables here. 45 centimeters, 65 degrees, 15 newtons. This is step 1 of the physics success blueprint, data extraction.
To solve this elegantly and secure every single method mark, we must follow a systematic process. The command word here would typically be calculate or determine, which means you must show you're working. Step 1, explicitly identify your force, which is 15 newtons, and your pivot, which is A. Step 2, we need to calculate the true perpendicular distance. Because the rod is at a 65-degree angle, the rod's length is not the perpendicular distance. We have to use trigonometry to find the horizontal distance from the line of action to the pivot. Step 3, we multiply the force by that newly calculated perpendicular distance. Writing out these steps, even briefly, guarantees you pick up partial marks even if you punch the wrong button on your calculator later. But wait, before you touch that calculator, heed this classic warning from the textbook because this is exactly where Sam rushes and fails.
The length of the rod was given as 45 centimeters. If you plug 45 into your moment equation, your answer will be completely wrong. Why? Because the standard SI unit for moments is Newton meters, not Newton centimeters. You absolutely must convert those 45 centimeters into 0.45 meters. Examiners deliberately use centimeters in the prompt to test your attention to detail. Don't fall for the trap. Always check your unit prefixes before doing the final multiplication.
Let's set up our final equation using our blueprint. We take our force of 15 newtons, we multiply it by the perpendicular distance. Based on the geometry of the right-angle triangle formed by the rod and the vertical line of action, that perpendicular horizontal distance is the hypotenuse, or 0.45 meters, multiplied by the sine of 65 degrees. So your paper should clearly show moment equals 15 times, open bracket, 0.45 times sine 65, close bracket. Showing this exact substitution is usually worth a standalone method mark in the Cambridge system.
And that satisfyingly yields our final answer, a turning effect of 6.1 Newton meters. By correctly decoding the command word, identifying the pivot, finding the true perpendicular distance with trig, and managing our time by catching the unit conversion early, we nailed it. This is the complete system: command word decoding, Peel framework application, and the time management matrix. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainer videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.
We've thoroughly mastered a single turning force today, and you now have the exact strategy to write the perfect exam response for it. But I'll leave you with this final, provocative thought to spark your curiosity and test your new skills. We just calculated one force pulling a rod down. But what if an object is perfectly balanced, with a completely zero resultant turning effect, while having 5 different forces acting on it from all angles? What does that tell us mathematically about all those interacting, competing moments? Think about how you would apply the PEL framework to explain that phenomenon. That is the incredible principle of moments, and it's your next step to mastering statics. Keep analyzing, keep practicing those perpendicular distances, and I'll see you in the next explainer.